All right, so we got one last section here of material for chapter 7. And the general topic here is what are called periodic properties. So it's properties of atoms or ions that we can relate to position in the periodic table. So one of the factors that we're going to want to account for is the electron configuration that we just talked about. How do the different filled levels and sublevels play into how easy it is to move electrons or how big the atom is or whatever. We'll go through a few of those. The other thing that we need to factor in addition to electron configuration and what's changing there, is a property called effective nuclear charge. So we know there's a charge associated with the nucleus based on how many protons are present in the nucleus, but the reality is the charge that an electron experiences depends on its environment, where it is with regards to the nucleus as well as with the other electrons close by. So there's a factor called Z effective. This would be the effective nuclear charge, and it's based on the actual nuclear charge, but then this other characteristic called a shielding factor. Now, we're not really going to calculate this. We're just going to need to evaluate how shielded is the electron we're looking at from the power of the positive charge of the nucleus. Now, just to give you an example here, real quick, say we've got, there's a nucleus with the positive charge, right? And again, in this cartoon picture, right, here's the 1s, there's some electrons there. Here's the 2s, there's some electrons there. Right? The electrons in the 2s orbital, they are experiencing the positive charge of the nucleus, but they're somewhat insulated from that charge by this intervening layer of electrons. So electrons are attracted to the positive charge, but they're also repelled by the negative charges of other electrons. So the electrons in the 1s experience more of the nuclear charge than the electrons in the 2s, and that would change how they are shielded from experiencing that actual charge. So you'd have a higher level of shielding for the 2s. As we move further and further away from the nucleus, the electrons experience less and less of that charge. And that'll be a factor we want to think about in terms of some of these properties. Okay? So let's jump in. The first property we want to think about is size. How big are atoms? And for a lot of these, we kind of want to think about, and I'm just going to use sort of a rectangle. Imagine this is the periodic table, right? It's missing a little bit of the detail, but we're looking for a general idea of properties here. Now, I think if we go this way, we go down the periodic table, this is one that's fairly straightforward, that people have a pretty good idea of what is going on. So say we're in the first column of the periodic table, we go from hydrogen to lithium to sodium to potassium. What's happening, each of those would represent an atom that has one electron in the s sublevel. So for hydrogen, it's 1s1, for lithium, it's 2s1, for sodium, it's 3s1, for potassium, it's 4s1. So we keep adding extra layers to those particular elements, almost like an onion, maybe a parfait or an ogre, but you add an extra layer and the atoms get bigger. So even though the nuclear charge is getting bigger, we're adding extra layers, those atoms are getting bigger. So as we go down, size increases. And as we go down the periodic table, the atoms get larger. So francium is much larger than lithium, right, at different kind of ends of that first column. Now, things are a little different as we go across, because you might expect the same thing. As you go across the periodic table, you're adding more to the element, more protons, more electrons, more pieces, but what happens as we go across the periodic table is size decreases. Right? And what we need to think about is why might that be the case, right? As we go down, it's increasing because of more layers. That's fairly straightforward. What happens as we go across, though, is we're basically adding electrons into the same layer. So if we think about lithium across to neon, right? 2s, 2, and then these are electrons going into the 2p. All the electrons are going into the second energy level. So we're not adding more layers. What we're doing is adding more protons to the nucleus. So going across, putting electrons basically in the same layer, but having a higher nuclear charge means that the positive charge of the nucleus can contract the existing shell of electrons. So size decreases across, right? And a good way to think of that is because of increasing nuclear charge. Right? So be particularly careful of that one because, yeah, your first instinct is going to be, well, that's got a higher atomic number. There's more protons, there's more electrons, there's probably more neutrons. That has to be bigger. That is not going to be the case if we're just going across. Now, here's an example problem based on that one. Arrange the following elements in order of increasing size. We've got aluminum, boron, carbon, potassium, and sodium. Right? The first thing we need to think about here is basically what layer are these elements in. So aluminum is in the 3p, boron is in the 2p, carbon is in the 2p, potassium is in the 4s, so fourth energy level, and sodium is in the 3s. Right? So increasing size, that means we want to start with the smallest and go to the biggest. The two smallest would be the ones that are in the second energy level. Only two layers in those atoms. So boron and carbon are going to be the smallest. What we have to figure out is which one would be smaller. Right? And if we look on the periodic table, right, boron's here, carbon's here. As we move to carbon, we are putting one more electron into the 2p sublevel, but carbon also has one more proton in its nucleus. That extra positive charge is going to be able to contract the electron shell of carbon a little bit relative to boron. So carbon's going to be the smallest. It's going to be smaller than boron. The next two would be the two in the third energy level, so sodium and aluminum. Right? Sodium's all the way over here on the left. Aluminum is more to the right. So similar idea there. Even though we're adding more electrons, we're actually going into the other subshell. Right? The increased nuclear charge of aluminum will be contracting the size of the electrons in the third energy level. So aluminum would come next, then sodium, right? And then potassium is the only element here that is in the fourth energy level. We're adding that extra layer on. That extra layer is really shielded from the positive charge of the nucleus, so potassium would be the biggest of our elements here. Okay. Now, maybe we can relate this to the size of ions as well. So I think maybe we can finish this page on the video. There will have to be a second video for this topic to get that last page. Right? What happens when we make an ion? So let's take, why don't we take sodium as an example here? And kind of in the middle, I'll use the neutral sodium. So neutral sodium would be 1s2, 2s2, 2p6, 3s2. No, I'm getting ahead of myself again. 3s1. Right? If we tried to make sodium an anion, that's when we'd add an extra electron, and it would be 1s2, 2s2, 2p6, 3s2. Right? And if we made sodium a cation, we're going to take away an electron. So sodium plus would be 1s2, 2s2, 2p6, and that's it. Nothing in the 3s. Right? Now, compared to the neutral anion, right? If we take away an electron, but we don't change the nucleus at all here, it's still a sodium nucleus. It's got the same number of protons, the same pull on the electrons. If there are fewer electrons, the nucleus can pull those in tighter because there are less electron-electron repulsions as you bring the electrons closer together. So the cation here is going to be smaller than the corresponding neutral sodium. The anion here, sodium minus, adding one more electron in is going to increase the way electrons are repelled by the other electrons. So an anion is always going to be larger than the corresponding neutral molecule. Okay, so that's one thing to think about. Cation is smaller, anion is larger for the same atom. The other place where ions are going to be interesting is when we have what is called isoelectronic elements. So let's add neon into the discussion here, because neon has the electron configuration of 1s2, 2s2, 2p6. That is exactly the same as we saw for sodium cation. 1s2, 2s2, 2p6. right? And it would also be the same as fluoride, a fluorine anion would have. We add one extra electron into fluorine, and it will also be 1s2, 2s2, 2p6. Now, how can we evaluate sizes here between these compounds? They've all got exactly the same electron configuration. The difference is going to be nuclear charge, right? What is the nucleus doing to kind of constrict or pull in that electron cloud? So the larger nuclear charge is going to be able to pull that electron cloud in more. So sodium has 11 protons, neon has 10, fluorine has 9. So the higher nuclear charge in this series, sodium would be the smallest, right? Neon would be in the middle, and the fluorine would be the largest. Because with equivalent electron clouds, right, it's actually going to be the pull of the nucleus that will determine their relative sizes relative to each other. Okay, I think we need to stop there. I've got an example here where we'll try to order the sizes of some ions here, but we'll do that one, and I think we can fit the last page in just one more video after this one.